We want to now look at what do we mean by mutually exclusive and collectively exhaustive events. So let's start with mutually exclusive events, right? We want to look at mutually exclusive or what we call disjoint events. So let's start with this, or disjoint events. Now the idea is that if for any two events, if for two events E and F, so we have these two events E and F, if for two events E and F, E intersection F is, sorry, if for two events E and F, E intersection F is equal to the null set, which you can write like this or like this. So both of these represent the null set, right? So if E intersection F is equal to the null set, if for two events, E and F, E intersection F is equal to the null set, which means they have no common outcomes. No common outcomes, then E and F are mutually exclusive events. So we are defining mutually exclusive events are those that the intersection is the null set, they have no common outcomes. Then E and F are mutually exclusive events. So we're saying that two mutually exclusive events are those that the intersection is the null set. They cannot occur at the same time or simultaneously, right? Because they don't have any common outcomes. When you perform a random experiment, you get exactly one outcome. So either event E will happen or F will happen. They both can't happen at the same time because there is no common outcome that they share. And we already looked at whenever you perform a random experiment, you get only one, you get exactly one and only one outcome. So it's either going to E that's going to occur or F that's going to occur. Neither of them are going to occur depending upon what outcome occurs, but they can't occur at the same time because they don't share any common outcomes. So they cannot occur at the same time or simultaneously. Let's look at an example. So the example is going to be we toss two coins. So the example is that the random experiment is that you're tossing two coins. And then we're defining, so let's just make it proper. So example is that the random experiment is we toss two coins and we define these events. So we have these events. E is both coins. So we're going to define these two events and we're going to show okay, there. I'm going to look at an example of two mutually exclusive events in this case. So the first event is going to be that a head appears on both of our coins. That's going to be our first event in this case. So both coins land on head. Both coins land on head. Right, so this includes head, head. And then F is going to be both coins land on tail. Right, so head on both coins, tail on both coins, right? Now, if I look at E intersection F, which we know, we already talked about when you're writing the intersection of two events, you can either write it with the intersection sign, which is the inverted U sign, or you can write it without the intersection sign as well, just as E times. And both of them represent E intersection F, right? Whether you write the inverted U sign or you don't, right? So it's equal to the null set, So then E intersection F, so E and F are mutually exclusive events. Right? They cannot occur at the same time. It cannot be the case that both coins land on heads and both coins land on tails. Because when you perform the random experiment of tossing two coins, either both land on head, both land on tail, or they land on something else. Like one lands on head, another lands on tail. So E and F are mutually exclusive events. Mutually exclusive. So this is what we mean by mutually exclusive events. So the events, so mutually exclusive events are those at the intersection is the null set. They don't have any common outcome, so they cannot occur simultaneously. Now let's look at collectively exhaustive events. So the next is collectively exhaustive events. So now if E union F is S, if for two events E and F, if for two events E and F, E union F, E union F is equal to S, where S represents your sample space, then E and F are collectively exhaustive events. So mutually exclusive events are those that the intersection is a null set. They don't have any common outcomes. They cannot occur at the same time. If for two events, the union is the sample space, then E and F are collectively exhaustive events. So the idea is that the union of the two events covers the entire sample space. Entire sample space. So let's look at an example of this. So now the random experiment that we're looking at is, okay, two dice are rolled, right? Let's look at two events. Let's define two events here. So E is going to be outcomes with sum less than 4. So it's outcomes with sum less than 4. So it has all those outcomes for which the sum is less than 4, right? So E is that event which has all those outcomes with sum less than 4. So now this could include the first I could have 1, the second could have 1, the first could have 1, the second could have 2, and then we could have first 2 and second 1. So this is E. F are going to be outcomes with sum greater than 4. Outcomes with sum greater than 4. So now this could be outcomes like it could be the first is 4 and the second is 1. And then it could be the first is 1, second is 4, and the first is 5, and second is 1, and so on. So you'll have all these outcomes, right? Then you have G, let's define G, which is outcomes with sum less than or equal to 4. Less than or equal to 4, right? So this would be 1, 1. This would be 1, 2, 2, 1. But since the sum can be 4 as well, unlike event E, we can also have here 3, 1. You can also have here 1, 3, and you can also have a 2, 2, right? So the difference between event E and G is in G, the sum has to be less than 4 of the outcomes. In G, it can be equal to 4 as well. So now we're here in this example, we'll note that E intersection F is equal to the null set, there's nothing in common. E has all those outcomes which would have a sum less than 4. F has strictly all those outcomes which have a sum greater than 4, right? So E intersection F is the null set, right? They don't share any common outcomes. The intersection is the null set. So E and F are mutually exclusive. Like we talked about mutually exclusive events, so E and F are mutually exclusive events because the intersection is the null set. They don't share any common outcomes. You can't roll two dice and get at the same time such outcomes that the sum is also less than 4 and the sum is also simultaneously greater than 4. That's not possible. G union F is equal to the sample space because see, when I take the union, we will get the sample space. The union will cover the entire sample space because F has all those outcomes, the sum is greater than 4. And G has all those outcomes for which the sum is less than equal to 4. And this is all the possibilities, right? Because here, E union F cannot be the sample space because this does not consider the outcomes for which the sum is equal to 4. Because the sum could be equal to 4, sum could be less than 4, sum is greater than 4. These are all the possibilities to cover the entire sample space. E has all those for which sum is less than 4. F has all those for which the sum is greater than 4. But the union cannot be the sample space because it's not covering all possible possibilities. One possibility is the sum could be 4. But G union F is equal to the sample space because all the outcomes, because regardless of whatever outcomes you get, The sum is either going to be greater than 4, in which case they'll be contained in F, or the sum is going to be less than equal to 4, in which case they're contained in G. So when you do F union G, you will cover the entire sample space, because all possible outcomes either fall in F or fall in G. Equal to S, so F and G are collectively exhaustive events. But note, F and G are not mutually exclusive, because F and G do have outcomes in common, those that have a, oh no, sorry, never mind. In this case, obviously they don't, yeah. So okay, so F and G are mutually exclusive in this case because you don't share any common outcomes. Because this is all outcomes with sum greater than 4, and this is all outcomes with sum less than equal to 4, so they can't share any common outcomes. So yeah, so F and G are both mutually exclusive as well as collectively exhaustive. E and F are mutually exclusive, but they're not collectively exhaustive because you're not accounting for sum is equal to 4. So let's just do one note and then we're done with this. Very few examples where events are both mutually exclusive and collectively exhaustive. Mutually exclusive and collectively exhaustive. An example is an event and its complement. So one example where an event is both mutually exclusive and collectively exhaustive is always going to be an example is an event and its complement. Both are mutually exclusive and collectively exhaustive. Right? Because if I take E intersection E complement, it's the null set because the complement is by defined as E complement is by defined as not E. It's all those outcomes that are in the sample space but not E, so they will not share any common outcomes because by definition E complement is not E, and the union will cover the sample space because E complemented include everything inside the sample space which is not inside E. So when you take the union, you have all the possible outcomes in the sample space, right? So if you look in the form of a Venn diagram, it's something like this. If this is E, this is E complement. So the intersection is the null set, they don't share any common outcomes, and the union covers the entire sample space. So an example or two events that are always mutually exclusive and collectively exhaustive is going to be an event and its own complement.